So I tried to get through before you guys get through all of it. What I want to do today, whatever, losers, is that I want to knock out, guys, I want to talk over people here. I want to go through all the different scenarios for word problems in 8.1, 8.2, and 8.3. It's actually quite easy. If there's any word problems that we have to deal with this year, these are going to be the easiest ones that we deal with. They really are. Now, we're going to talk about growth and decay. We're going to talk about principal and interest and compounding interest style problems. A lot of times for most of these things, it's going to wind up having to utilize your calculator correctly. So please make sure you have your calculator. If you haven't, if you need to charge real quick from charging, that we help the juices as we go along. But a lot of this stuff is going to be going through. What's up? No, too many papers. I should have called that. But I made the concept. So, growth. Ladies and gentlemen, growth models. When we talk about this stuff, we're going to look at what are called growth models, and then we're going to look at something called a decay model. They're very, very similar. And a lot of times with these types of problems, you're going to be given specific information, and then you have to take something from that information to decipher what in the world is going on. Now, what I did with this unit is that I took a bunch of the actual notes, and I just made them on a sheet. And the reason that I did that is because there are so many words with things. I figured that by having these pre-printed for you, you can throw them in your 3-ring binder, you can staple it to your notebooks and whatnot, and I just kind of shrunk it so they fit on one sheet. And I kind of did the same thing with the homework sheet that we'll do here later on as well. That way we have the in front of us, because you know how many times we've done word problems, you guys are like trying to write down what in the world I have on the board, and I'm just kind of going through it. So here I'm trying to help you out. So, Merry Christmas. You're welcome. I look out for your well-being. Sometimes. Ken Moss? Those Pompelis? No, not those Pompelis. All right. So, here's what we got. We're going to use what's called, you know what's here? Oh, you could have given them, I'll get it from Internet today, all right? You get what's called an exponential growth model. Exponential growth models are very simple to work with. Every single one of them kind of looks the same. You have this value of A, which is your initial amount. This value of R is your rate, and they put the rates as a decimal. And this value of T is time, and it's usually in years. More often than not, it's time in years. So what you're going to be looking at here is you've actually, in chemistry, if you've done radioactive decay at all, I know you do at some point in time. It's all it is an exponential growth problem, but it's decay. And the only difference between growth and decay, instead of it being a plus, it would be a minus. Because what happens here is that if you think about what exponential growth looks like, it was y equals a b to the x, and growth was when b was greater than 1. This is creating b is greater than 1 by adding a decimal to it. It'll create decay for b being less than 1 but greater than 0 when I take 1 minus a rate. That's how it's so very similar to what you've already done, but you're working with a couple extra percentages. So if you know how to take 6% and turn it into 0.06, you're going to be fine. Unlike me, I kept putting 6% as 6.6 because, I can't math. I'm afraid that I scared you. My English is not so good. The only weird thing they talk about is this value that's called 1 plus r, the jump that's in the parentheses, is called a growth factor. So if you have an example, I think the very next one to the right talks about a population example. That population example states that the population of Winnie Manuka, I do too, is modeled by this formula of P equals 6191 times 1.04 T, where T is the number of years since 1990. So therefore, year 0 is 1990. What is the initial population in the year 1990? 6191. Therefore, your initial amount is 6191. Your growth factor to this. The growth factor is the whole thing that's in parentheses. The growth factor is the 1.04. What is the rate of increase? 4%. It's at a rate of 4%. That's what you're looking at being able to do. Remember, the growth factor is 1 plus your rate. So 1.04 is 1 plus 0.04, which means 0.04 as a percent is 4%. All right. Now, if I wanted to take this value and figure out, well, what would my population estimate to be in the year 1998, what would I do? I put that to the t-value of 1998, 8. Here we go with that. I could also ask approximately what year was the population 10,000. You look at your Y value in your table. Look for where it hits 10,000. You can approximate a year. It's super, super easy to work with these things, guys. It really, really is. Okay. Yeah? I think I got these out of sequence for some reason. Thought I had another example of that on here. No, appreciation. Oh, never mind. No, we don't have to. Yeah, that's decreased though, because they're in danger. They're probably decreasing. But we'll worry about that one in a minute. All right, let's talk about something fun. Let's talk about money. Bank accounts. Now, a lot of times when you deposit money into a bank, it talks about this thing called compounding interest. Banks use this formula of what's called, actually, this is a very simplified formula. No, it's not your notes. I'm just explaining what it is. What compound interest means is that every time that you, let me rephrase this. You guys understand if you put money into a bank, into a savings account, it earns interest? Albeit it's super small amount of interest. You're not earning a lot of money on it and whatever. Yeah, it's a savings account unless you have lots of money on it, you're not going to earn a lot of percentage on it. But for a rough example, if you put, I think an example in here that I have coming up, well, we'll get to it. If we do $1,000, and if you start with an initial amount, well, here's the formula. Your overall amount will be equal to this thing called principal. Principal is your initial amount, how much you give the bank. It'll be times the quantity 1 plus the rate divided by the number of times it compounds. Number of times it compounds times how many years. Here's what all these values mean. P is initial amount. Rate is your percent as a decimal. N is number of times compounded. What that means is if you compound something annually, how many times a year does it compound? Once. If I compound something quarterly, how many times does it go? 4. If I compound something monthly, how many times would it go? If I compound daily, what would it be? A lot, 365, and so on and so on. So this thing that, yes, sir? And, yeah. Number of times compound, yep. What's that? For both parts? Yes. Mm-hmm. Yep. And that's what happens here. I'm going to show you what happens with it. It's super, super easy to do. Okay? And then T, again, is going to be time in year. It's generally in years. Now, when you're dealing with this thing called compounding interest, I think the next example talks about depositing $1,000. So here's a really easy scenario to think of. Let's say you got really, really, really lucky when you were born, and somebody deposited in your family $1,000 into a savings account for you that compounded so many times. We'll talk about different compounding parts at 8%. 8% never happens, but let's just say it did. Okay. So you have an initial amount of $1,000, and you have a rate of 8%. When you graduate, you're generally about 18 years old, and you can get to that money. It's not like a trust fund. Now, I want to show you the difference it means in the number of times something compounds to how fast something increases in money that you'll have on hand. So if we talk about the number of times compound, if I say that it compounds annually, so one time a year. If I say that it compounds monthly, if I say that it compounds daily, and then let's get super crazy, hourly. Well, I want to show you what the differences are. The formula itself then doesn't change. We're going to use this compound interest formula where we have your principal, your initial amount, 1 minus the rate, number of times compounded, number of times compounded, number of years. So what I do is this. This is really nice calculator work. I type in, I did do a plus, I don't know why I didn't show up. So it'll be 1,000 parentheses 1 plus 0.08 over first one be 1 times 18. And then what I do is move this over so I can. What I do is that I take my calculator, I do 1,000 parentheses 1 plus alpha y equals 0.08 over 1, close my parentheses, to the 1 times 18, and I hit enter. Which means if it compounds just annually over the course of 18 years, I'd wind up with $3,096.02. Because you remember, we're talking about money here, so we round the nearest cent, which would be 100. Did any of you guys see the movie Office Space? Really? You guys have a 3-day weekend. You have 2 things to do. Add an Office Space. All I'm asking you to do. Okay? Oh, it's actually right. There might be a quiz. I'm going to put a quiz about that. But seriously, the movie Office Space was about 98, 99, something like that. And the whole premise was that they were rewriting bank software for the year 2000. Back in the day, they didn't realize that years needed to be in a 4-date format. They just said, oh, it's 88, 89, 99. They're like, holy crap, it goes back to 00. We're back at, we got to change all the software. So they went back and redid all this code of the software, but then they realized that when you're banking, you get all these thousands and millions and small little increments of decimals. Where does those fractions and fractions of cents go? I got an idea. Let's make an account. We'll send all of it to my account. That's the premise of the movie. It's absolutely fantastic. It's rated R, so you have to get your parents' permission to watch. Or you can find it on TV from time to time. They bleep out like every other word. It's a riot. It is so good. Anyway, so that's what it looks like if you go annual. When I change that, what was the next one I said? Let's do monthly. That means all I have to do is go back and, you guys know how to overwrite your equations? Go back and overwrite your equation to change your n values to 12s. What you're going to do is, all right, I know I'm going to do a 12, so I'm going to see how my cursor is blinking on the multiply part. I'm going to hit second, insert, 2. And then I just back over and I do the same thing with the denominator. Oh, I just went up, up, enter. Did you get it? I did monthly. Did I skip quarterly?
Yeah, quarterly.
Okay. What's that? Oh, that's okay. I just wanted to show you as it gets larger quicker. Oh, I'm sorry. You want to get up here on how many hours are in the and then put that in. That'll be your end because it's going to think about how many times it does it per, how many hours are in a year, and then you multiply that times the 18. So your end value would be 365 times 24, and then you multiply that again by 18 for the next one. And I'll show you how it looks. Second.
Okay.
Sir. Oh, there you go. If I do that again, we did monthly. If I do it daily, it's not much of a difference, is it? If I do 365, you get the point here. When you do hourly, it's a lot, isn't it? So if I do hourly, I can still rewrite this expression quickly. 1,000 parentheses 1 plus alpha y equals point. Yeah, I know I did that earlier. 0.08. It'd be 365 times 24 to the 365 times 24 times 18. So you're thinking like, oh, it's compounding like all the time. The value really changing? Right, and that's the thing. And this goes into the idea of where this value, this magical mythical value of E comes into play. Remember yesterday I told you guys that the value of E is an approximation as a growth rate as the number of times something compounds approaches infinity? That's why this happens. Put this in real quick. 1,000 E is right here where, oh, there it was. E is the button that hits second ln, log of the natural log. And now it goes up there. What was our rate for this problem? 0.08. And how many years were we doing it for? As something compounds continuously, that's where E comes into play, you're not going to get any different. E is the button you hit second ln. The button kind of next to 4. I just wanted to show you, that's where this E function comes in. Yesterday we had talked about that value of E is an approximation of, that value of E to the x is approximately 1 plus r to the n as n approaches infinity. So as this gets, n values get larger and larger and larger, it's approaching E. And that's where this comes from. Growth. Only thing you have to be able to tell the difference here is if you're putting money into a bank account, it says you're compounding quarterly, annually, semi-annually, daily, whatever, and you're using that formula. If it's set, yes. I will give you equations, but I will not tell you which is which. If it gives you something that says compounding continuously, then you'll use something different, and we'll get to that here in a second. But banking stuff is super easy. It's literally plug and chug. The craziest thing you might have to solve for is, let's say you needed to figure out how much do you have to invest to get so much money at the end. And it's super easy. You just work everything backwards like an equation. Right? You can use the table too, but you'd have to know how to set that up correctly. All right, it's really simple. Going with this one then goes into, well, I just did that. I'm ahead of this. I'm ahead of this. Balance. Is the next little quick one is the, actually, you know what? Let me skip ahead. If it's something called compounding continuously, if it compounds continuously, this is the last formula on this sheet. It's the last one. We'll do decay last. If you're compounding something continuously, your amount is equal to your principal e to the rate times. I don't know where it is. Somewhere in the back. All I'm showing you is that this is the formula. Without a sequence. Where again, p. Yep. So if it says it's something is compounding continuously, you use the PERT formula. If it says it's compounding annually or semi-annually, then you use the rate over n to the nt. That's the only difference here, guys. Compound continuously is PERT. The other one is the other one. So your R is again your rate as a decimal, and T 9.5 times out of 10 is time in years. Okay. They are really easy to work with. Not too bad. So that gets us to be able to talk about what's called a decay problem. Your decay problems then when we had exponential decay, it was a, b to the x, where b was smaller than 1 but bigger than 0. But we're talking about growth models, like, so it's exponential decay in terms of a decay model. It's going to be, excuse me, it's 1 minus your r, where the value of r is your rate, again, as a decimal, which therefore generates, this is kind of like the b value that's between 1 and 0. So you're going to have your, still is your a is your initial amount. AL. R is your rate as a decimal, and T again is time, generally in years. The thing that's in parentheses, instead of being a growth factor, it is now called a decay factor. Very good. What's that? What? L? Sorry. Yeah. So this value here, the 1 minus r, stuff in parentheses, it's called the decay factor. So if I have 0.83, I have 0.83 as my decay factor, what's my rate? That's all you're looking at. That's about as much math you'd have to do in your head. If your decay factor is 0.83, that tells you you have a rate of 17%. But do I need to use that 17% for anything if they give me a decay factor? Yes, sir. What do you mean? Oh, for a number of times? No. Nope. These are problems that you see that are called depreciation. You guys heard that before? Depreciation. Things that depreciate are, if you think about a depreciating asset, A depreciated asset is a car. Okay. You know, when you buy a brand new car, the moment you drive it off the lot, it's worth less than what you purchased it for. More often, unless you're talking about specialized things here and there, but for the most part, that's what happens. So, one of the things that I tell students about this time of year is that most of you guys are generally sophomores. You're starting to go through driver's ed. You start thinking, some of you guys start getting licenses. Some of you guys have licenses. Some of you guys are borrowing cars and all that. You're thinking, ooh, maybe with my summer job, I would save some money and buy myself a car. Well, when you go to buy cars, whether they're brand new or used, one of the things you always want to look into is how fast that style or type of vehicle depreciates. Is it going to be worth so much money in 4 or 5 years when you might want to get something new, or is it be worth effectively poop? Okay. Now, if you go through and you start thinking about what types of cars depreciate faster than others, there are some types that do that quicker. A lot of times, Chryslers and not Wranglers, those have a value forever, but some of the Dodge things, the Dodge and Chrysler, those tend to have the highest depreciation rates. Fiats, those little bar thingies, and little smart cars, those things depreciate like almost instantaneously. You look at things that don't depreciate as fast. Diesel trucks, heavy-duty trucks hold their value. They do. It's weird. My wife had a TDI Jetta. She had a TDI Jetta, which was a little four-door Jetta that had a diesel engine in it. That car held its value forever. Subarus hold their value forever. It's one of those things. Honda Accords, Honda Civics, those small cars like that, they tend to hold their value better than other types. So as you start to think about vehicles, what you're looking at, it's not a bad idea to have something that holds its value. Because what happens over time, if you spend 20 grand on a used car, and in only 3 years you've only paid off, you still owe another 16,000. Well, let's say the car might only be worth 12. If they're only going to give you $12,000 as a trade-in, and you owe 16, that means you still owe another $4,000. You guys ever heard the term being underwater? A lot of mortgages have been like that for a long time because your house is worth less than what you owe on it. The way the depreciation works. Okay. So as you go through these steps, I never miss you. So when you get into problems like these, you're looking at the idea of, the example I have on your sheet here. If you buy a new car for 24 grand and that car depreciates at 16%, write the model and let's figure out what it's worth in 2 years. And then let's use our calculator to estimate how many years did it take for it to be worth $12,000. Now, obviously, cars aren't going to automatically depreciate and go all the way to zero. At some point in time, they're going to level out and still be worth something because they're metal and plastic and stuff. You can recycle them at least. So if I have an initial amount of 24 grand, my rate is 16%, so I put that as a decimal, it would be 0.16, so it would be 1 minus 0.16, and then my model would be T for years. That's all I have to do. I don't have to take 1 minus 0.6 and write it down. I just leave it like that because my calculator has buttons, and I like buttons. They're fun. So you literally go to your calculator now. Y equals. Hey, it's convenient I had that problem in there. I know, who would have thunk it, right? So I want to know what this is going to be worth in 2 years. So if I type that into my Y equals, the easiest, and then I know later on I had a question that asked me after about how many years this is worth 12 grand, I'm just going to automatically go to my table. I put this in because for any one of these types of growth or decay models, I'm never going to have you graph that by hand because those graphs just look like crap. They're so hard to do, and there's no reason to do it. You have a calculator that has a table. You should just know how to use it. We'll just learn how to use it. Bless you. If I go to my table, after 2 years, that car is worth $16,900. So I know that that car is worth $16,934. When T equals 2, it's worth $16,932. 34. Big time. And then I think it said the next part was approximately after how many years was it worth 12 grand? Well, careful. See how as you scroll down, as you scroll down, look in the Y column where it crosses over to 12,000. Between 3 and 4 years. So after 4 years, it was worth about 12 grand. Did you get it after 17? You might have typed in something. See how easy you're just utilizing the calculator to go back and forth with these things. Okay. Yeah, that's exactly what I say. Yes, ma'am. No, ma'am. I'm never going to ask you to graph one of these. I'll say approximately after how many years, and that's your clue to go to table. These types of problems are a lot of times are going to be table problems. Speaking of, I did the same thing with every single word problem off these 3 sections. Instead of having to open up 3 different PDF files to go through everything, I just put it all on one sheet. You guys are young. Your eyesight's somewhat decent. I got context too. I get it. Try to knock out as much as you can. Let's knock out as much as you can as you go through this. As much as this looks like it's a lot, these are quite really fast. Yes, sir. There's a bunch. There's a good 15, 20 of them on there, but more often than not, they're just. I do. I read that. Yeah, you should be able to get through 85% of that tonight. We'll talk about where we're at and see how much more we need to do tomorrow. But those. Yeah. I didn't, like I said, don't do anything that says graph. Because there's no reason to. Because if it says graph the function, that means you're probably just going to put it in the table and look and see where you have to find. These are, as much as this looks like there's a lot going on here, on the floor for it. Yes. Yes. It's formula work. You're pressing buttons on a calculator. Seriously.